Picture a cave, somewhere in the world, late Ice Age. Outside, the climate is shifting, glaciers are retreating, and the last of the megafauna are disappearing one by one. Inside, in the darkness, something died, and then it stayed there. For 16,000 years, give or take, the bones just waited, buried under layers of sediment, sealed away from everything, perfectly preserved in the cold, dark silence. Then someone found them, and that's when things got strange. Because when researchers actually looked at these remains, measured them, compared them, ran them against every database of known human populations they had, the bones didn't match. Not Cro-Magnon, not Neanderthal, not any archaic human species already on the books. The proportions were off. The morphology was wrong in ways that were hard to explain away. The remains dated to around 14,000 BC, which should be recent enough that we know exactly what kind of humans were walking around. We don't have gaps that late. Except, apparently we do. That's what this video is about. Now, before you get too deep into this, if you're watching at some strange hour because you can't sleep, I genuinely want to know. Drop a comment right now. Tell me where you are and what time it is there. I read these. It's one of my favourite things. You've got people in Tokyo at sunrise, people in Toronto at 2 in the morning, all watching the same weird mystery unfold in real time. So tell me where you're at. Back to the cave. The question at the centre of this whole story is deceptively simple. Whose bones are these? And the answer, frustratingly, is that nobody is entirely sure. There are several competing explanations, and none of them are completely comfortable. Maybe these were members of a previously unknown population, a late Ice Age lineage that survived far longer than anyone suspected before quietly vanishing, around 14,000 BC. Maybe the bones were distorted by pathology, or unusual developmental variation that just looks exotic, but is still fully human. Maybe the dating is off, or the deposit was mixed, or there was a misidentification somewhere in the analysis. Maybe, and this is the least satisfying option, someone got it wrong, and there's nothing unusual here at all. We're going to work through all of it. We'll start with the world these people would have lived in, then move to how the discovery actually unfolded, how caves record time in their geology, how scientists dated these remains, and then the bones themselves, what exactly looks wrong and why that matters. We'll dig into the actual methods researchers use to determine whether bones are human, how ancient DNA either solves these questions or refuses to cooperate, and then we'll go through every serious alternative explanation one by one. And finally, we'll sit with the most unsettling possibility, that something was here, something human enough to bury or be buried, and then it was simply gone. The mystery is real, the uncertainty is real, and the cave is still out there, still keeping its secrets. Let's start at the beginning. To understand why these bones matter, you need to understand the world they came from, and that world was nothing like the one we live in now. 16,000 years ago, Earth was finishing up one of the most dramatic climate episodes in the last million years. The last glacial maximum had peaked around 26,000 years ago, and by 14,000 BC the planet was thawing, slowly, unevenly, in ways that completely reshaped every landscape on every continent. Glaciers that had buried northern Europe, northern Asia, and large chunks of North America under ice sheets a mile thick were retreating. Not smoothly, not predictably, but retreating. And the world left behind was alien in ways that are hard to picture. Sea levels were roughly 120 meters lower than they are today. Let that sink in. The coastlines we know now, the ones on every map, every globe, every satellite image, those didn't exist. Entire regions that are now underwater were dry land. What we call the North Sea was a vast plain. Indonesia was connected to mainland Southeast Asia in a massive landmass researchers call Sunderland. Britain was attached to continental Europe. You could walk from Siberia to Alaska. The geography of human migration was completely different, which means our maps of where people were living are also, at best, incomplete guesses based on whatever survived. The climate itself was a patchwork. In some regions, steppe tundra stretched for thousands of miles, cold and dry but not lifeless. Mammoths, woolly rhinos, cave lions, giant deer were still out there, though their numbers were dropping. In other regions, forests were beginning to return as temperatures climbed. River systems were rerouting. Lakes were filling and draining. The landscape was in motion in ways that happened too slowly for any individual to notice, but fast enough to completely transform ecosystems within a few generations. This is the backdrop. Now let's talk about who was living in it. By 14,000 BC, anatomically modern humans had already been on the move for tens of thousands of years. Homo sapiens had left Africa somewhere around 60,000 to 70,000 years ago, spread across Asia, reached Australia by at least 50,000 years ago, pushed into Europe and displaced or absorbed the Neanderthals, and crossed into the Americas somewhere in the window between 20,000 and 15,000 years ago. By 14,000 BC, our species was essentially global, not densely settled, not even close, but globally distributed in small scattered groups, living off whatever the land provided. Here's the thing though, the story wasn't as clean as that summary makes it sound. Neanderthals had gone extinct somewhere around 40,000 years ago, probably a combination of competition, climate stress and interbreeding that gradually absorbed them into the expanding modern human population. The Denisovans, that mysterious eastern branch of archaic humans, had likely disappeared as a distinct group on a similar timescale, though their DNA kept turning up in modern populations across Asia and the Pacific, which tells you the disappearance was never as total as the word extinction implies. And there were others. The Flores hominin, sometimes called the Hobbit, had survived on the Indonesian island of Flores until perhaps 50,000 years ago in an almost impossibly isolated environment. No, maybe longer. The Red Deer Cave people in southern China show features that look archaic by modern standards and survived until possibly 11,000 years ago, far later than anyone expected. The picture emerging from the last 2 decades of paleoanthropology is not one clean line of human progress. It's a tangle, multiple lineages, overlapping in time and space, sometimes interbreeding, sometimes competing, sometimes disappearing into the archaeological record without a clean explanation. Which brings us to caves. Caves are, in the most literal sense, time machines, not because of anything mystical, but because of simple geology. When sediment accumulates on a cave floor, it tends to stay put. Wind doesn't scour it away. Rain doesn't wash it out the same way it would on an open hillside. Animals den in caves and die in caves, and their bones get buried in place. Humans shelter in caves, use them for burials, for storage, for ritual, and when they leave things behind. Layer by layer, season by season, century by century, caves build up a stratigraphic record that preserves time in a way almost nothing else on the surface can match. That's why so much of what we know about ancient humans comes from caves. Not because ancient humans were particularly cave-obsessed, but because caves are where the evidence survives. A small group using a single cave for even a few generations can leave material that outlasts empires. A burial, a hearth, a fragment of worked bone. Given the right conditions of temperature, humidity and chemistry, those fragments can survive 16,000 years in almost perfect condition. Which means a group that left almost no trace anywhere else in the landscape can still show up, in startling detail, in a single cave deposit. And this creates an interesting problem, because small groups leave small samples, maybe a handful of individuals, maybe just 1 or 2. And when you're working with a sample that small, it becomes genuinely difficult to know what you're looking at. Is the unusual morphology a population-level trait? something this whole group shared? Or is it individual variation, one person who happened to look different for reasons that had nothing to do with their ancestry? Is the date reliable, or was the deposit disturbed? Are you looking at a completely unknown human lineage? Or are you looking at the edges of normal human diversity expressed in a few individuals who happen to end up in the same cave? These are not rhetorical questions, they are the actual questions, and the answers are not obvious. So here's the frame for everything that follows. At 14,000 BC, the world was in flux. Sea levels were rising, climates were shifting, ecosystems were reorganizing. Homo sapiens was everywhere, or close to it. But the edges of that everywhere were blurry and contested. Other lineages had mostly vanished, but mostly is not the same as completely. And in the geological record tucked into the darkness of cave deposits across the world, there are still surprises waiting. The cave at the centre of this story is one of them, and what was found inside it forces a question that's harder to answer than it sounds. How different do bones have to look before you stop calling them human and start calling them something else? We're about to find out. Stories like this one rarely begin in a laboratory. They begin with someone who isn't a scientist noticing something that doesn't fit. The cave had been known to locals for years before anyone with academic credentials showed up to look at it seriously. That's not unusual. Across Southeast Asia, across Europe, across every region where the karst geology carves limestone into hollow spaces, local communities have always known about the caves in their landscape. They shelter in them, store things in them, tell stories about them. Sometimes they pull bones out of them, bones that look old and strange, and those bones circulate as curiosities, as conversation pieces, as things that get passed around and pointed at before anyone thinks to write anything down. By the time a researcher hears the rumour and follows it to the source, the chain of custody is already complicated. The first formal reports described a deposit that looked promising. Stratified sediment, signs of ancient habitation, charcoal from old fires, animal bones mixed with what appeared to be human remains. On the surface, that's a fairly standard cave archaeology scenario. Caves across this entire region have produced exactly that kind of assemblage. Layers of human occupation stretching back thousands of years, sometimes tens of thousands, readable like a slow and imperfect diary of who was living where and when. Researchers had every reason to expect something familiar. What they didn't expect was what the human bones actually looked like when they came out of the ground. The excavation itself was complicated from the beginning, and this matters more than it might seem. Early excavation conditions shape everything that comes after. When bones come out of undisturbed sediment in controlled conditions, with precise documentation of exactly where each fragment was found, at what depth, in what relationship to surrounding material, you have a solid foundation for every subsequent argument about dating and context. When conditions are less controlled, when material is moved before it's fully documented, when the early recovery involves people who are more excited than methodical, gaps open up that never fully close. Critics will find those gaps. They always do. And sometimes the gaps are legitimate problems, not just rhetorical ammunition. The first people to examine the bones at the site level noted immediately that something was off. The proportions weren't sitting right. Modern human skeletons have a particular suite of features that become almost intuitive to researchers who spend careers working with comparative anatomy. The relationship between limb length and body mass, the shape of the jaw, the thickness of the cranial vault, the way the brow ridge does or doesn't project over the eye sockets. These features cluster in predictable ways in modern Homo sapiens, and they cluster differently in archaic species like Neanderthals or Homo erectus. What was coming out of this cave didn't cluster cleanly in either place. Specific features that drew attention immediately included robustness where modern humans are typically gracile, proportions that suggested either an unusual body plan or individuals who had undergone severe physical stress across their lifetimes, and certain cranial characteristics that, depending on who you asked, looked either archaic or simply outside the normal range of modern human variation. The bones were not obviously the remains of a known archaic species, but they were not obviously modern either. They sat in an uncomfortable middle space that made everyone who looked at them want to reach for an explanation. The remains were removed for analysis, photographs were taken, measurements were made, casts were produced in some cases, and then the material began moving through the academic ecosystem, which is where things get interesting in ways that are not always flattering to science as an institution. Early examination by a small number of researchers produced preliminary assessments that circulated informally before anything was formally published. This is normal. Science runs on conversation, on hallway discussions at conferences, on emails between colleagues who trust each other's judgment. But preliminary assessments are exactly that, preliminary. They're made without full analysis, without complete comparative data, without the rigorous statistical treatment that distinguishes a defensible claim from an educated impression. And sometimes those preliminary assessments are more dramatic than the final data supports. In this case, the early characterizations were striking enough that they escaped the informal network and reached a wider audience before the careful work was done. That's a pattern with a long history in paleoanthropology. The hobbit fossils from Flores produced headlines about a new human species before the scientific community had reached any kind of consensus. The Denisovan announcement was genuinely extraordinary, but was also met with immediate skepticism from researchers who wanted to see the full dataset. Red Deer Cave produced similarly premature excitement. Sensational claims have a gravitational pull that careful analysis, with all its qualifications and confidence intervals and peer review, struggles to match. So by the time formal publication began, the story was already running ahead of the evidence. Some researchers were using language that implied a completely separate and previously unknown human lineage had been found. Others, who hadn't yet had access to the primary material, were already pushing back, arguing that unusual morphology in a small sample is not the same thing as a new species, that variation within Homo sapiens is wider than popular understanding suggests, and that extraordinary claims require extraordinary evidence before anyone starts rewriting the textbook. Both camps had legitimate points. That's what makes this worth paying attention to, because the discovery story is never just about the bones. It's about how knowledge gets made, how it gets complicated by the conditions of recovery, how it gets shaped by who sees the material first and what frameworks they bring to it. The bones themselves are sitting there, silent, carrying whatever information they carry regardless of who's arguing about them. But before we can talk about what the bones actually show, we need to understand the ground they came from, and that means going back into the cave itself. If you walk into that cave today, what you see with your eyes is almost useless at first glance. You see a floor, maybe some rocks, a slope of dirt in one direction, a darker stain near the back wall that someone tells you used to be a hearth. To an untrained visitor, it's just inside of cave. To an archaeologist, it's a sliced open time machine. The first thing to understand is that a cave floor is not a floor. It's a stack, a vertical pile of events, one on top of another, compressed into sediment. Every layer is a moment, or more realistically, a long blurry interval, in which gravity and water and biology and human behaviour all conspire to drop material in one place, and then more or less leave it there. More or less. Because the second thing to understand is that caves hate staying simple. The textbook version of cave stratigraphy is clean and reassuring. People occupy the entrance. They drop ash and bone and broken tools on the ground. Dust and soil slowly blow or wash in. Bats leave droppings from the ceiling. A flood occasionally brings a pulse of new sediment. Over time, you get a neat sequence, older at the bottom, younger at the top, each layer a page in a book. The real version is messy. Limestone caves are carved by water, and they continue to be shaped by water long after humans first walk inside. During heavy rains, water seeps through cracks, drips from the ceiling, or, in some systems, surges through as a subterranean stream. That water can erode sediment from one part of the interior and dump it somewhere else. It can undercut a slope so that the upper material slumps downward, folding layers that used to be horizontal into strange curves and jumbled pockets. It can pick up tiny bones, charred wood, and stone flakes and redeposit them all together in a spot where no human hand ever placed them. Then there are collapses. Over tens of thousands of years, rock spalls off the ceiling and walls. Big blocks fall, smashing into whatever was underneath, driving artifacts down into older layers or punching holes where later material can trickle deep into the sequence. In some caves, whole sections of the roof give way in a single event. You can see these as chaotic zones in the stratigraphy, places where the normal order is disrupted and everything looks churned. Adding to the chaos are the living creatures that treat the cave as home long before and long after humans. Porcupines dig, rodents burrow, carnivores drag carcasses into corners to eat in peace. Each of them moves bones. A hyena can haul a limb from outside, kill sight into the cave, chew on it on a ledge, and leave it to fall into a gap. A small burrowing mammal can excavate a tunnel that lets a piece of bone from an upper layer drop into material that's thousands of years older. Over time, these countless tiny disturbances stitch the layers together in ways that only look simple on cross-section drawings. Humans do their part too. People who return to the same shelter over generations don't politely stay on top of yesterday's floor. They dig fire pits. They scoop out shallow hollows for sleeping. They dig latrines or rubbish pits. But they bury their dead. Every one of those actions cuts through older material and introduces new pockets of younger sediment inside older layers. This is how bones move. You have the obvious mechanisms: floods washing remains from outside into the cave and then onward to a lower chamber. Sediment slumps that send a compacted block of older material sliding sideways or downward. Rockfall smashing a burial and scattering fragments downslope. And then you have the biological ones. Scavengers pulling bones out of shallow graves, burrowing animals pushing them up or down or sideways, insects and plant roots slowly weakening and displacing them. On top of that, once archaeologists and collectors arrive, yet another layer of disturbance begins. Early digging, especially if it isn't carefully planned, can remove support from a section so that adjacent sediment collapses. Or someone working without a clear grid might follow a concentration of bones laterally, undermining layers and allowing material to roll and mix. The moment a deposit is touched without documentation, you've created a puzzle whose original picture can never be fully reconstructed. This is why context matters as much as the bones themselves. A femur on a table in a lab is just a shaped piece of mineralized collagen. Its dimensions can tell you something about body size, about muscle attachments, about taxonomic affinities, but they tell you almost nothing about life without context. Was that individual living in a cold phase or a warm one? Were they eating mostly large game or a mix of small animals and plants? Were they part of a large, stable community or an isolated band camping in a marginal refuge? To even begin answering those questions, you need associations. You need to know whether that bone came from a layer with hearths, concentrated charcoal, ash, reddened sediment from repeated fires. You need to know whether stone tools were present, and if so, what kind? Heavy core tools? Delicate blades? Microliths that suggest complex composite weapons? You need to know what animal bones were in the same layer. Are we talking about deer, pigs, water buffalo, fish? Are the bones burned, cut-marked, broken in patterns that show marrow extraction, or are they carnivore-gnawed? You also look for pigments, ochre staining, fragments of worked bone or shell, beads, engraved pieces. These become the fingerprints of behaviour. If the strange bones come from a layer with a fully modern human-style toolkit, dense evidence of structured hearths, and ornaments that look like those found at other late Pleistocene sites, that's one kind of story. If they come from a layer with a very different technology, unusual fauna, and no clear modern analogues in the region, that's another. The danger is when those lines get blurred, and they get blurred all the time. Yeah, one of the most common gotchas in cave archaeology is mixed deposits. Imagine a slope inside the entrance. For a few thousand years, people camp near the back, dropping ash and bone. Then, centuries later, a flood undercuts the slope and sends a tongue of that older material sliding down, where it settles on top of even older sediment. From above, after the slope stabilizes and accumulates new dust and debris, you now have a layer that looks coherent, but is actually a mix. Older hearth debris and younger trickle-in, sitting on top of something older still. If you dig straight down with a shovel and treat that whole zone as one level, you might end up with human bones, animal remains, and tools that never actually belonged in the same occupational phase all bagged together. It's not that anyone is fabricating data, or it's that the cave has edited its own archives, and careless excavation lets the edit pass for the original. The other big trap is intrusive burials. For tens of thousands of years, people have treated caves as good places to put the dead. Sometimes they lay bodies on the floor. Sometimes they dig into existing sediment. From a stratigraphic point of view, a grave cut is a wound, a vertical shaft slicing down through older layers, filled with younger material and a skeleton. If you miss that cut, if the outline of the grave wall is faint, if the sediment infill looks similar to the surroundings, you can mistakenly record that skeleton as belonging to the deeper, older level it passes through. Suddenly, a 14,000-year-old burial seems to be sitting in a layer otherwise dated to 30,000 years. Or, Holocene skeleton has miraculously appeared in a Pleistocene deposit. In some famous cases, this exact process created decades of debate, before more careful re-excavation showed that the supposedly ancient humans were intrusive, younger than the sediments they pierced. So, when someone claims a strange human species vanished from a cave around 14,000 BC, the first question a cautious researcher asks is not, what do the bones look like? It's, how good is the context? An ideal excavation, the kind that would give this story the strongest possible footing, is almost obsessively documented. The team would establish a precise grid across the cave floor, dividing the space into squares and sometimes sub-squares. Every piece of sediment removed would be recorded by square and by depth, in centimetres. As layers change, colour, texture, compaction, presence of ash, stone or bone, the excavators would define new stratigraphic units, drawing profiles that show exactly how each unit relates to the next. Every bone larger than a fingernail would be plotted in 3 dimensions: how far from the entrance, how far from the side wall, how deep below an established datum. The orientation of long bones would be noted. Are they aligned along a slope, suggesting gravity movement? Cross-cutting a slope, suggesting in-place deposition? Are they grouped in anatomical order, as in a burial, or scattered as in a secondary deposit? All sediment would be sieved, preferably through fine mesh, to catch tiny bones, teeth, beads, and microflint that the eye can miss. Charcoal fragments suitable for radiocarbon dating would be sampled in situ from hearths, or not just scooped from loose soil. Where possible, blocks of intact sediment would be removed for micromorphology, thin section analysis under a microscope that can distinguish between say ash fallen from an ancient fire and material reworked by water long after the fire went out. Photographs and detailed drawings would capture the position of each hearth, each concentration of tools, each cluster of bones. The boundaries of any suspected grave cuts would be traced, their fills excavated separately from the surrounding matrix. Samples for pollen, phytoliths, and other environmental proxies would be taken from sealed, undisturbed layers to reconstruct the landscape outside at the time each layer formed. When the bones that started this whole controversy were lifted from the cave, an ideal record would tell you, unambiguously, does something like individual X found in primary burial, cut into layer 4, which overlies layer 5 dated to 16,000 years ago and underlies layer 3 dated to 12,000 years ago. Associated with late Pleistocene stone tools of a specific type and with fauna characteristic of that climatic phase. That kind of chain of evidence pins a skeleton firmly to a moment in time and a cultural context. Break that chain through movement, mixing, poor recording, and suddenly the ground under every dramatic interpretation starts to shake. In this cave, the one with the not quite modern, not quite archaic bones, that chain is exactly what we have to inspect. Because before we can argue about whether these individuals were truly something outside our known human family tree, we have to be sure we're not just looking at ghosts created by geology, gravity, and a less than perfect excavation. Which brings us to the next question. How do we actually put dates on this layered chaos and say, with any confidence at all, that the vanishing happened around 14,000 BC? If you ask 10 people, when did this mysterious population vanish? And they all answer, about 14,000 BC. It sounds solid. It sounds like a fact. But that number isn't carved into a cave wall. It isn't printed on the bones. It's the end result of a chain of assumptions, corrections, cross-checks, and occasionally hopeful guesswork. To see how strong or how fragile that 14,000 BC really is, you have to follow that chain all the way back to its first link. That first link almost always is radiocarbon. Radiocarbon dating works because the universe is rude to nitrogen. High-energy cosmic rays smash into atoms in the upper atmosphere and occasionally turn ordinary nitrogen-14 into radioactive carbon-14. That carbon-14 behaves, chemically, just like regular carbon. Plants breathe it in as CO2. Animals eat the plants. You eat the plants and the animals. As long as you're alive, you're part of this global carbon circulation, constantly topping up your internal supply of carbon-14. The moment you die, the supply cuts off. No more carbon-14 comes in. The stuff already in your tissue starts to decay, ticking down at a known rate. Its half-life is about 5,730 years. Measure how much carbon-14 is left in your bone collagen or in a piece of charcoal from your last campfire. Compare it to the level in the atmosphere and you get an age. At least that's the elegant textbook version. In practice, especially for late Ice Age dates, there's a catch. The amount of carbon-14 in the atmosphere hasn't been constant through time. Solar activity, Earth's magnetic field, even changes in the carbon cycle all nudge the production rate up and down. If you just take the raw radiocarbon result, say 12,000 radiocarbon years before present, and treat that as a calendar year, you're wrong. Sometimes a little wrong, sometimes thousands of years wrong. That's why calibration matters. Over the last few decades, scientists have built calibration curves using things that grow in layers we can count. Tree rings, for the last 14,000 years or so, layers in corals and stalagmites, valved lake sediments. Now each layer is a known calendar year, and it contains carbon. By comparing the radiocarbon in those layers to their actual age, you can map how radiocarbon time stretches and compresses relative to calendar time. When you hear 14,000 BC for a Pleistocene cave, what that usually means is the lab reported a radiocarbon age, maybe 12,500 plus or minus 80 years before present, measured in uncalibrated radiocarbon years. Then someone ran that number through a calibration program with the latest curve and got a probability distribution. Maybe the most likely calendar age range fell around 16,000 to 17,000 years ago. Subtract from present, by convention, 1950, and you get something like about 14,000 BC. Already you can see the layers, raw count, calibration curve, probability range, rounded narrative date. Now ask, what exactly did we date? In a cave like this, the usual candidates are bone collagen, charcoal, and sometimes shells. Bone collagen is the holy grail. It's part of the bone's organic matrix and, if preserved, gives you a direct clock from the organism itself. Date the collagen from the strange bones, and you get the age of that individual. No, maybe this fire pit is the same age, hedging, but collagen is fragile. It dissolves in acidic soil, breaks down with heat and moisture, and is easily overprinted by later carbon. If the bone has been in a damp cave for 14,000 years, gnawed, moved, soaked, dried, it might have almost no original collagen left. Lab screen for that. Looking at nitrogen content, carbon to nitrogen ratios, the telltale chemistry of intact collagen. If those indicators are off, the date is suspect from the start. Charcoal is often plan B. Burned wood is mostly carbon. If you find a chunk firmly embedded in an intact hearth, it can be an excellent target. But charcoal has its own traps. The old wood problem, for one. If the people in this cave were burning dead branches from a centuries-old tree, you might date the lifetime of the tree, not the night of the fire. Usually that's a modest offset, but in some environments with very slow-growing trees, it can be bigger than you'd like. Shells can also be dated, especially in coastal or riverine caves where people ate mollusks. The issue there is reservoir effects. Marine organisms get some of their carbon from dissolved ancient carbonates in seawater, which can make them appear hundreds of years, sometimes more than 1,000 years, so older than they really are if you don't account for it. Freshwater shells can be even worse depending on local geology. On top of the inherent quirks of each material, there's the ever-present spectre of contamination. Carbon is everywhere. Modern rootlets weave through ancient sediment. Groundwater carries dissolved carbonates. Conservators in the 1920s brushed bones with shellac or glue, both made from organic material that can introduce modern or random carbon into a sample. A single drop of modern organic contamination in a sample that's supposed to be 14,000 years old can shift the age by centuries. This is why old museum samples are such headaches. Imagine a femur excavated in 1910, washed in tap water, dried on a windowsill, labelled in India ink, maybe consolidated with some unknown resin. You have then stored in a wooden cabinet that outgassed volatile organic compounds for 100 years. Now, in 2020, someone drills into it for collagen and sends the powder to a radiocarbon lab. Even if the lab is meticulous, it can only remove contamination it knows how to detect. Carbonates dissolved by acid washes, humic acids removed by alkali treatments, clear consolidants removed with solvents. Some residues, especially old conservation chemicals that have partly penetrated the bone, are much harder to strip away completely. The risk is that you get a nice precise number that's precisely wrong. So, how do you avoid hanging your entire 14,000 BC vanishing on one potentially compromised sample you cross-check? One powerful independent method is uranium series dating. When water-rich and dissolved uranium percolates through a cave and deposits calcite, stalagmites, stalactites, thin flowstone layers. It also locks in tiny amounts of uranium. Over time, uranium decays into thorium at a known rate. Measure the ratio of uranium to thorium in that calcite layer, and you get an age. If you have a thin sheet of calcite that formed on top of a bone, its uranium series age gives you a minimum. The bone must be older than that. If a layer of flowstone lies between two sedimentary units with bones, its age brackets them. Combine that with radiocarbon from charcoal in the same units, and you start building a scaffold of constraints rather than relying on a single plank. Then there's stratigraphic correlation. If this cave sequence includes a distinctive tephra layer, a thin ash from a known volcanic eruption, you can compare that to other sites where the same ash has been dated. More often, archaeologists rely on packages of evidence, a specific style of stone tool, a certain combination of animal species, a recognizable pattern of hearths and activity areas that matches other well-dated sites in the region. Associated fauna are particularly useful in the late Pleistocene. If the layer with the strange bones also contains bones of animals that went extinct around the last glacial maximum, that's one kind of signal. If it contains species known to appear only after the ice sheets retreated, a certain kind of deer, a specific rodent with well-studied range shifts, that's another. None of these things, radiocarbon, uranium series, stratigraphy, faunal association, stand alone as absolute truth. Each has error bars, unknowns, and potential biases. But when they converge, confidence grows. So how solid is a date range, really? Think of three categories: solid, shaky, and misleading. A solid late Ice Age date for a human presence would look something like this. Multiple radiocarbon dates on short-lived materials, like twigs or seeds, from a well-defined hearth, all overlapping when calibrated. At least one direct date on bone collagen from the same stratigraphic unit, with good collagen quality indicators. A uranium series bracket from calcite immediately above or below, and faunal and artifact assemblages that fit what we know of the region at that time. In that scenario, when you say, these people were here around 14,000 BC, you're not leaning on a single slender reed. You're standing on a lattice of independent lines of evidence, all pointing into the same narrow window. Shaky is when some of those pieces are missing or ambiguous. Maybe there's one good charcoal date from a hearth near the bones, but the bones themselves haven't yielded collagen. Maybe the calcite bracket is wide, spanning several thousand years. Maybe the stone tools fit a broad technological tradition that lasts for millennia. You can still suggest a range, but you have to acknowledge it as a range, not a sharp moment. Misleading is the danger zone. That's when a single uncalibrated radiocarbon date on a questionable sample, charcoal collected from a mixed layer in the 1960s, or a poorly documented bone, gets repeated in paper after paper and slowly hardens into fact. It's when later studies find conflicting dates, but those are quietly set aside because they complicate the story. It's when nobody goes back to the surviving material with modern methods to see if the old number holds up. What would really strengthen confidence in the 14,000 BC vanishing in this cave? Fresh, carefully targeted dating. Direct radiocarbon dates on multiple individuals' bones, screened for excellent collagen preservation. Parallel dates on associated hearth charcoal from sealed, clearly defined layers. Uranium series ages on overlying and underlying calcite to bracket the occupational horizon. A coherent pattern in the associated fauna and artifacts that matches other well-studied late Pleistocene sites in the region, not just vaguely, but in detail. If all of those aligned around the same few centuries, then around 14,000 BC would be more than a convenient tagline. It would be a defensible claim about when these unusual people last used this cave. Until then, that date is a hypothesis, not a revelation. And that matters. because what you think happened to them depends entirely on when you believe they lived. A vanished population at 14,000 BC faces a very different world and very different neighbours than one at 24,000 or 9,000 BC. So with the clock, for now, only partially nailed down, we can finally turn to the bones themselves. What is it about their shapes, their proportions, their details, that made some researchers whisper that they might not belong to any humans we currently recognise? When you strip away the drama, the headlines, the YouTube thumbnails with glowing red eyes, what do we actually have in this cave? Bones. Some whole, some shattered, some so worn down they're barely more than hints of what they used to be. Let's start there. The collection isn't a complete skeleton laid out neatly on a burial platform. It's an anatomical jigsaw puzzle scattered through several layers of sediment. There are cranial fragments, parts of the vault, pieces of the face, occasional bits of the base where the skull meets the spine. There are mandibles, lower jaws, though not all of them with the teeth still in place. There are loose teeth by the handful, some clearly human, some more ambiguous at first glance. From the postcranial skeleton, the stuff below the skull, we have long bone shafts from arms and legs, a few proximal and distal ends where they formed joints, fragments of pelvis, vertebrae in various states of preservation, and a smattering of ribs and hand and foot bones. Some elements are beautifully preserved. The texture of the cortical bone is crisp. Muscle attachment sites are clear. Sutures in the cranial vault can be traced. Those are the pieces that attract the most confident pronouncements. Others are a mess, gnawed, weathered, cracked by repeated freeze-thaw cycles, infiltrated by minerals that have swollen and distorted them. In those pieces, subtle anatomical markers can be blurred or exaggerated, turning an ordinary feature into something that looks bizarre. So when you hear claims that these remains don't match any known human, understand, nobody is saying every single bone is alien. The argument hangs on a subset of elements that seem, even to experienced eyes, to sit uncomfortably at the edges of what we expect for Homo sapiens. To see why, we need to talk about what those expectations are. When physical anthropologists compare a skeleton to known humans, they're not looking for some vague, does it look human, vibe. They're checking specific landmarks and proportions that have been documented in thousands of individuals from dozens of populations. On the skull, they pay close attention to overall cranial shape. Is the brain case long and low? Like many archaic humans, or high and rounded like most modern Homo sapiens? How pronounced is the forehead? Brow ridges? Are the supraorbital tori, the arches of bone over the eyes, thin and broken into segments, or thick, continuous bars like you see in Neanderthals and earlier species? Mid-face projection? Does the area around the nose and upper teeth jut forward, or sit relatively flat? Occipital region. At the back of the skull, is there an occipital bun, a torus, or a more globular shape? Cranial capacity and vault thickness. How big is the brain case and how thick is the bone itself? On the lower face. Mandible shape. Is the jaw robust or gracile? Does it flare outward at the gonial angle? How tall is it? Chin. This is a big one. Modern humans have a true mental eminence, a protruding chin, or many archaic humans don't. Dental arcade. Are the tooth rows U-shaped, V-shaped, or more parabolic? How wide is the palate? Then there are the teeth themselves. Crown size and shape. Are the molars big or small? Do they taper in a certain pattern from first to third molar? Root configuration. How many roots? How they're fused? Their curvature. Enamel thickness and wear patterns. How fast they wore down and how. Below the head, the checklist continues. Limb proportions. How long are the arms relative to the legs? Within each limb, how do the segments compare? Humerus to radius, femur to tibia. Robusticity. How thick are the shafts? How large and pronounced are the muscle attachment sites? Joint surfaces. Shape of the hip socket, knee joint, ankle, shoulder, elbow. Pelvis width. Shape of the iliac blades. And birth canal dimensions. Curvature. Taken together, these markers let you say with varying degrees of confidence, this is a modern human, this is a Neanderthal, this is something else, or we can't tell from what's left. So what made some researchers pause over these cave bones? Several traits have been highlighted as unusual. Remember, we're synthesizing a set of reported oddities here. Different teams focus on different details, but the broad picture looks like this. First, the cranial fragments. Where enough of the vault can be reconstructed, the skulls are reported to be a bit long and low compared to typical late Pleistocene Homo sapiens from nearby regions. The foreheads slope more than expected. The bones over the eyes in some individuals form thicker, with more continuous brow ridges than modern comparative samples from the same broad time window. That alone doesn't make them non-human. There are early Homo sapiens with fairly robust brows. There are population-level differences, but when you combine that with the second feature, a face that seems more projecting in the mid-face than you'd predict for their age and region, it starts to look a little more archaic. Some reconstructions suggest a subtly inflated nasal region and a slight forward projection of the upper jaw, hinting at something between classic modern human flatness and Neanderthal mid-facial projection. Not a full Neanderthal face, but not the textbook modern either. Then there's the question of chins. A few mandibles reportedly show weak or absent mental eminences. Instead of a sharp, protruding chin, the front of the jaw slopes more gently, or even retreats slightly. Again, this is not unheard of in Homo sapiens. You can find modern individuals with receding chins, but if a significant fraction of jaws in a single assemblage lack a strong chin, and other features also skew archaic, the pattern becomes more interesting. Dental traits round out the cranial oddities. Some of the molars appear relatively large and robust compared to late glacial modern humans in the surrounding area. There are hints of root and crown forms more often associated with earlier or non-African populations. Three-rooted lower molars, shovel-shaped incisors, enlarged third molars that don't show the usual size reduction trend we see in many Holocene groups. Again, each of these traits exists somewhere within modern human variation. But the cluster, if it's real and not an artifact of sampling or preservation, raises eyebrows. Below the neck, the story gets stranger in a different way. The long bones, where measurements are possible, suggest a combination of relatively short lower limbs with quite robust shafts. Femora that are thick relative to their length. Tibiae that are stout with strong muscle attachment markings. The proportions in some reconstructions hint at shorter legs for a given estimated body height than modern local populations, edging toward the stocky build we associate with cold-adapted humans like Neanderthals. There are also reported oddities in joint morphology, hip sockets that are deep and broad, knee joints that look over-engineered for heavy loading, shoulder joints with large articular surfaces relative to shaft size. All of that points to powerful musculature and high physical demands. Put all these pieces together, slightly archaic cranial vaults, robust brows, weak chins, big teeth, stocky limbs, and you can see how someone invested in the idea of unknown humans could start making bold claims. But there are two big cautions we have to layer on top of this. First, preservation bias. Which bones survive best? The densest ones. Robust jaws stick around longer than delicate facial bones. Thick, long bone shafts endure where gracile ones crumble. Over tens of thousands of years, the fossil record naturally accentuates the heavy-duty parts of a population's anatomy. That can make an average group of humans look more robust than they were in life, especially if the graceful outliers simply didn't fossilize well. Second, human variation is enormous. Modern Homo sapiens are not a single neat cluster of measurements. We're a sprawling cloud. There are living populations with relatively long, low crania, others with quite pronounced brow ridges, individuals with weak chins, groups with robust limb bones shaped by genetics, lifestyle, or both. If you cherry-pick the most extreme individuals from different modern populations and lay their bones out side by side, you can easily create a monster that looks like it shouldn't belong to our species. A marathon runner's femur next to a powerlifter's humerus, a skull from a cold-adapted high-latitude group next to a jaw from a population with unusual dental traits. The composite would scream non-human to anyone relying on intuition. Anthropologists know this. That's why, in serious work, they don't stop at "it looks different to me." They quantify. They measure dozens, sometimes hundreds of dimensions on each bone, lengths, widths, curvatures, angles. They compare those numbers to massive reference datasets of known Homo sapiens, Neanderthals, and other hominins. They run statistical analyses that ask, where does this bone fall in multivariate space? Is it an outlier within Homo sapiens? Does it overlap Neanderthals? Does it sit between? The bones from this cave, the ones causing all the excitement, have mostly not been through that full gauntlet yet. Some measurements exist, some plots have been made, but in many cases the claims you hear, they don't match any known humans, are still based heavily on eyeballing, on mental comparisons to what experienced researchers have seen before. Experience matters. But our eyes are biased. We remember the weird ones. We forget the boring normal ones. We're drawn to patterns that tell a good story. So the real test for these bones is still ahead of us. Rigorous morphometrics. Can we take the skull fragments, the jaws, the teeth, the limb bones, and drop their measurements into the same statistical space as hundreds of late Pleistocene Homo sapiens, plus Neanderthals, plus Denisovan inferred morphologies where we have them? Do they cluster with known humans, just at the edge of variation? Do they overlap Neanderthals or other archaic groups? Or do they carve out their own, stubborn little island in the data, forcing us to consider the possibility that something more unusual really did walk into that cave around the end of the Ice Age? That's where we're heading next. Away from impressions, toward numbers, away from "it looks weird to me" toward "here's where it sits in the map of human anatomy." So how do you actually test that map? How do you go from "this jaw feels odd in my hands" to statistically, this specimen sits 3 standard deviations away from any measured human population? You start with something very unglamorous, calipers and tape measures. For most of the history of physical anthropology, analysis meant linear measurements. You'd measure the maximum length of a femur, the bizygomatic breadth of a face, cranial height from earhole to vertex, mandibular thickness at the symphysis. You'd record angles, how steeply the forehead rises, how the jawline turns at the gonial angle. You'd take breadths and depths at standardized landmarks defined in measurement manuals so that anybody, anywhere, could replicate them. Then you'd build ratios, length versus breadth, height versus circumference, indices that capture shape in a crude but surprisingly informative way. Is this skull long and narrow or short and wide? Are these limbs relatively short for their diameter? Are these teeth large relative to the jaw? On their own, these numbers are just a spreadsheet. The magic happens when you line them up against reference data. For modern humans, those datasets are enormous. Thousands upon thousands of individuals from around the world, measured across the 20th century, archived in museum collections and digital repositories. You can pull cranial metrics from East African foragers, 19th century European farmers, indigenous Australians, Arctic populations, tropical islanders. Yet you can capture a huge slice of what Homo sapiens can look like. For Upper Paleolithic and Late Glacial humans, the people living around and just before 14,000 BC, we have fewer specimens, but still enough to define a cloud. Skulls and skeletons from Europe, the Levant, Siberia, East Asia, bits of North Africa. They form a comparative baseline for late Ice Age Homo sapiens. Then you add Neanderthals. Their reference set is smaller, dozens of fairly complete individuals rather than hundreds, but their anatomy occupies a distinct region of morphospace. Long, low vaults, massive faces, stocky bodies. You don't need many measurements before their cluster pulls away from recent humans. Denisovans are a different story. We don't have a shelf full of Denisovan skulls. We have a handful of bone fragments, some teeth, a mandible from Xiahe on the Tibetan plateau, a few postcranial pieces, and a lot of DNA. Their known morphology is like a sketch with half the lines missing. Still, even that sketch matters. Those big, peculiar Denisovan molars, that robust Xiahe jaw, they carve out a tentative region other fossils can be compared against. So, in an ideal world, here's what you'd do with our cave bones. You'd collect every traditional metric you can, cranial lengths, breadths, and heights, from the vault pieces that fit together, facial widths and heights where the fragments allow, mandibular measurements, body height, thickness, symphysis angle, dental crown diameters and root dimensions, limb bone lengths and midshaft diameters, articular surface sizes at the joints. And you'd input those into software that already knows what thousands of other humans and a few dozen Neanderthals look like in exactly those measurements. Then you'd hit run. The program doesn't think in the way we do. It doesn't say this looks Neanderthalish. It takes the combined pattern of all those dimensions and drops each specimen as a point into a multivariate space. A cloud of Homo sapiens, a cloud of Neanderthals, a few lonely points for Denisovan-like jaws and teeth, and then our cave points. If the cave bones fall smack in the human cloud, the story's basically over. They might be a bit robust or gracile, but they're comfortably within variation. If they overlap the edge, a little beyond most moderns but still touching the Upper Paleolithic humans, that's more interesting but not shocking. Think of them as weird, but still cousins. If they consistently sit closer to Neanderthals or lie between the human and Neanderthal clouds, that opens up a whole different set of questions. Hybridization, archaic survival, regional continuity. And if they're off on their own, not clustering with any known group, that's when people start whispering about unknown lineages. But here's the catch. Bones are not abstract points in space. They're broken, warped, incomplete objects, and all of those messy realities leak into the numbers. That's why, in the last couple of decades, a new toolset has become essential: 3D scanning and geometric morphometrics. Instead of just taking a handful of lengths and breadths, researchers now digitize entire bones. Laser scanners, structured like rigs, micro-CT. These capture the surface of a jaw, the curve of a vault, the topology of a tooth in millions of points. From that cloud you can place precise landmarks, tiny coordinate systems at consistent anatomical locations. Geometric morphometrics doesn't just say, this skull is 18 centimeters long. It says given 60 landmarks and semi-landmarks across the skull, here's the exact way this bone is bent, curved, and bulged in 3 dimensions compared to others. It strips away overall size if you want, focusing on pure shape. It lets you visualize differences, how the average cave mandible would have to morph to become the average late glacial human jaw, or a Neanderthal one. The references have gone 3D as well. We now have digital collections of Upper Paleolithic skulls, Neanderthal crania, Holocene humans from across the globe. As even fragmentary fossils can be aligned and compared if enough overlapping landmarks are available. So for our mysterious cave bones, The cutting-edge test isn't just, is the chin 25 millimeters thick? It's, when I superimpose this jaw onto a global sample of jaws in 3D and let the computer find the major axes of shape variation, where does this specimen land? When a specimen falls outside known clusters in this kind of analysis, it doesn't mean it's a different species automatically. It means the combination of traits it carries is rare or absent in the samples you used. But that sentence hides a problem. The samples you used. Comparative data sets are only as good as what we've dug up and decided to measure. Neanderthals are overrepresented from Europe and Western Asia. Upper Paleolithic humans are better known from certain caves and burial sites than from open-air camps. Many regions of the world, especially in the late Pleistocene, are almost blank on our anatomical map. Add to this the fact that our cave assemblage is fragmentary. A long bone shaft with both ends missing carries less information than a complete femur. A jaw with broken tooth sockets tells you less than one with intact dentition. Reconstructing a cranium from shattered vault bones involves choices. Which fragments belong together? How much to correct for warping? How to align pieces that don't meet perfectly anymore? Every choice is a potential bias. Fill in a missing piece by mirroring the other side and you might accidentally modernize an archaic trait, or the opposite. Smooth a warped surface so landmarks can be placed, and you might push a specimen deeper into or out of a cluster. Small sample sizes amplify this. If you have 5 mandibles from the cave and they all look a bit odd, is that a new population signal? Or is it just that randomness handed you 5 individuals from the tail of normal variation? Maybe all male, all with heavy chewing loads, all from one extended family with a quirk of jaw shape. Statistics can tell you how far from the mean they fall in your reference set. They cannot on their own tell you why. And then there's the moving target problem. Our concept of normal Homo sapiens is not fixed. It shifts as new fossils are added, new regions are excavated, new populations are measured. Traits once thought weird and archaic sometimes turn out to be common in undersampled groups. Those big, complex molars you might be tempted to call non-human. In some cases, they show up in perfectly modern populations once you start looking. Some chin shapes we used to treat as almost Neanderthal turn out to sit at the margins of normal variation in certain regions. The reverse happens too. A fossil originally shoehorned into sapiens because we lacked better options can drift toward Neanderthal or Denisovan space as fresh comparative material fills out those clusters. We've already seen this play out. Specimens that look like outliers 30 years ago have been gently pulled back into the human cloud by more comprehensive data sets. Others, once considered boring sapiens, now sit suspiciously close to archaic clusters in reanalyses. So when someone says, these cave bones fall outside known humans, you have to ask 3 questions. Outside which humans? Modern global samples, or just Europeans from the 1800s? Outside which time slice? Are we comparing late glacial foragers to 20th century urban populations shaped by different diets and lifestyles? And outside based on what? A handful of linear metrics, or a dense 3D landmark analysis? The more you refine those questions, the less dramatic the phrase outside often becomes. Sometimes outside shrinks to barely overlapping the edge. Sometimes it dissolves entirely once you include, say, Central Asian Upper Paleolithic crania that weren't in the original reference. And yet, ambiguity cuts both ways. If, after you've thrown everything at the problem, dense 3D morphometrics, or broad comparative samples including Neanderthals and Denisovan-like jaws, careful checks for reconstruction bias, the cave specimens still refuse to sit comfortably in any known cluster, that stubbornness means something. It might mean an unusual local population of Homo sapiens with a distinctive anatomy. It might mean heavy environmental shaping, extreme diet, extreme activity. that pushed bones into less explored corners of shape space. Or, in the most provocative reading, it might hint at a lineage that had been weaving in and out of contact with other humans, leaving traces in our DNA but never before seen so clearly in bone. To sort those possibilities, morphometrics alone isn't enough. Bones tell us shape. DNA tells us ancestry. So the next question is obvious. Can we get ancient DNA out of these 14,000-year-old bones? And if we can, will the genetic story match the anatomical mystery or tear it apart? Whether we can or not depends on something very unromantic: chemistry. Caves can be incredible time capsules for DNA, and they can also be molecular graveyards where genetic material goes to die. What ancient DNA needs most is stability. Cool, relatively constant temperatures, moderate dryness, limited oxygen, not too many microbes chewing through every organic molecule they can find. Some caves, especially deep, dry ones with steady airflow and little water intrusion, are perfect. Bones there can sit for tens of thousands of years with their DNA fragmented, yes, but still readable. Other caves are the opposite: seasonal floods, dripping water dissolving minerals and washing in new microbes, temperature swings near the entrance, bat guano piling up and turning the floor into a biochemical war zone. In those environments, collagen gets eaten, fats oxidize, and DNA breaks into pieces so small and chemically altered that, for all practical purposes, it's gone. At 14,000 BC, our cave is relatively young in Paleolithic terms. That's good news for DNA. Our Neanderthal genomes have been sequenced from bones more than 100,000 years old. Denisovan DNA has come out of fragments even older. In theory, 16,000-year-old remains should be a sweet spot. Old enough to be interesting, young enough that DNA has a chance, but in theory is doing a lot of work. The same climate that shaped the people living in and around the cave also shaped what happened to their molecules after death. If these bones lay in a cool, dry, protected chamber, the odds of recovery are decent. If they spent millennia near the drip line, soaked on and off by groundwater, or colonized by fungi and bacteria, the best sequencing machines on Earth may see nothing but noise. So how do you actually find out? It starts with the scariest step for any curator: drilling into the fossil. Ancient DNA labs pick the densest, best preserved parts of a bone or tooth, often the inner ear region of the temporal bone, or the cementum on tooth roots. Those are microenvironments where DNA sometimes shelters from the outside world. You take a tiny sample, maybe a few tens of milligrams of powder, trying to balance information gained against damage to an irreplaceable specimen. But the real battle isn't just extraction, it's contamination. Modern human DNA is everywhere. On your skin, in your breath, embedded in the dust of the museum where those bones have sat for decades. A single fingerprint carries orders of magnitude more intact DNA than a 14,000-year-old femur fragment. So ancient DNA labs are built like clean rooms. Positive air pressure so outside air doesn't drift in. UV lights to break down stray DNA. There's bleach washes on every surface. Researchers suit up in full protective gear. Hoods, masks, double gloves, working in spaces that have never seen modern DNA amplification before. The workflow is almost paranoid by design. You take the bone sample in a dedicated ancient lab. You include extraction blanks, tubes that go through every step with no bone at all, to show what contamination the process itself introduces. You use freshly sterilized tools for each specimen. You keep pre-PCR and post-PCR areas completely separate, because amplified DNA is like glitter. It gets everywhere and never leaves. Once you've dissolved the bone mineral and teased out whatever DNA is left, you build sequencing libraries, short fragments tagged with little molecular barcodes so the machines can tell which red came from which sample. Then comes the sequencing itself. Modern high-throughput platforms don't aim for one gene at a time. They take everything, human, bacterial, fungal, environmental, and read it in millions or billions of tiny snippets. What you get back is not a genome, it's a soup of fragments, a mixture of ancient and modern, target and background. The critical step is authentication, deciding which pieces really belong to an individual who died 16,000 years ago, and which belong to people who have handled the bones, microbes that colonized them last century, or even lab workers who thought they were being careful. Ancient DNA carries a calling card. Over time, certain chemical changes accumulate at the ends of molecules, most famously cytosine bases deaminating to look like thymine. That leaves a characteristic pattern, an excess of specific substitutions at fragment tips. The DNA is also short, often only 40 to 80 base pairs long, far shorter than modern contamination. So bioinformaticians look for exactly those signatures. They align reads to reference genomes, then ask, are these fragments the right length distribution? Do they show the expected damage pattern? Are they present in far higher proportion in the bone extract than in the blank controls? If the answer is yes, you can be reasonably confident you're looking at authentic ancient molecules. Then the real question comes into focus. Whose molecules are they? From here, there are a few broad possibilities for our mysterious cave bones. 1. The DNA looks like regular Homo sapiens. It clusters cleanly with other late Pleistocene humans from nearby regions. It shares the usual mix of ancient variants seen in Eurasian populations of that time. Maybe it carries small amounts of Neanderthal or Denisovan ancestry, as almost all non-African humans do, but nothing shocking. In that case, the genetic evidence would be saying, whatever makes these bones look weird, it isn't a deeply divergent species. These were people well within the sapient family tree. 2. The genome, or even partial genome, leans archaic. Instead of falling snugly among known Upper Paleolithic humans, it starts edging toward more ancient branches. It might carry an unusually high proportion of Neanderthal ancestry, or segments that look most similar to Denisovan sequences, or, most intriguing, stretches that don't match any known archaic genomes well. That's where phrases like ghost lineage start appearing in papers, a population that contributed genes to us but is not yet represented by a name skeleton. 3. Admixture. The DNA might be a mosaic, clear Homo sapiens overall, but with chunks that are unmistakably archaic. That's not hypothetical. We've already seen individuals who are literal first-generation hybrids, like the Denisovan Neanderthal offspring from Denisova Cave. For our site, that could mean this group was part of a frontier zone where different human lineages were interbreeding, creating exactly the kind of anatomical combinations that look strange in morphometric analyses. Or 4. Nothing. No usable DNA. The sequencer sees almost no human reads with authentic damage patterns, or what little it sees is indistinguishable from low-level contamination. Fear you can run more, enrich for mitochondrial DNA, try different bones, but the result is the same. The chemistry just didn't cooperate. That 4th outcome is more common than the headlines suggest. You only hear about the spectacular successes, complete Neanderthal genomes, high-coverage Denisovan sequences, Ice Age hunter-gatherers with crisp ancestry profiles. For every one of those, there are many projects where months of careful lab work end with a shrug and a thin supplemental table. No authentic ancient human DNA recovered. And this is where interpretation gets dangerous. A no result is profoundly unsatisfying. It tempts people to fill the void with story. If the bones look odd and the DNA doesn't speak, it's easy to slip into. Maybe the reason we can't get DNA is because there's something else. Some unknown hominin so divergent our methods can't catch it. But that's not how the technology works. The failure mode of ancient DNA is not too alien to read. It's too broken, too scarce, too overprinted by microbes and modern contamination. If our cave specimens yield no genome, all we've learned is that this particular combination of preservation environment, handling history and laboratory technique wasn't enough. The mystery hasn't been solved, it's just remained opaque. However, in the last decade, a different line of evidence has changed what no DNA in the bones really means. Because you don't actually need bones to detect who was in a cave. Every time a person, or an animal, uses a space, they shed genetic material. Skin cells, hair, bodily fluids, feces, tiny fragments of tissue that drift into the dust and get trapped in the sediment. Over thousands of years, that debris can build up a molecular record of presence, even if the actual skeletons are gone or unidentifiable. This is environmental DNA, sediment DNA. Researchers can take small cores of cave floor sediment from carefully dated layers, extract whatever DNA remains, and then use targeted enrichment to fish out fragments that match mammals, or more specifically humans and their relatives. That's how Denisovans were identified in layers where no diagnostic bones were found at all, just their genetic shadow in the dirt. For our 14,000 BC cave, this means we're not limited to the questionable handful of odd bones. Even if the skeletons themselves are too degraded, the sediments embedding them might preserve a community snapshot. We could ask, in the layer where the non-human bones appear, do we see Homo sapiens DNA, Neanderthal DNA, any signal of Denisovan-like sequences? Are there shifts in the genetic signatures up and down the stratigraphy that mirror changes in tool types or faunal assemblages? Sediment DNA isn't perfect. It's even more fragmented than bone DNA, more mixed, more vulnerable to movement between layers. But it's independent. It can reveal, for example, that a level with weird bones is saturated with perfectly ordinary Homo sapiens DNA, and nothing else. Or conversely, that a layer with anatomically normal-looking remains carries a surprising trace of archaic ancestry, invisible in the skeletons themselves. When you put it all together, ancient DNA is both our sharpest and our most fragile tool. At its best, it slices clean through the fog. This individual was a late glacial Homo sapiens, descended from these ancestral populations, carrying this much archaic ancestry. Or, this bone belongs to a lineage we've never seen before in the flesh, but whose genes still flicker faintly in some of us today. At its worst, it breaks in your hands and tells you nothing. So, as we imagine testing the cave bones, we have to live with all four possibilities: clear sapiens, clear archaic signal, hybrid mosaic, or silence. If the genomes talk, they'll either tame the anatomical strangeness or amplify it. If they don't, we're pushed back onto bones, tools, context, and the more mundane, but often more plausible explanations for why skeletons can look strange without belonging to a lost species, which means our next step isn't deeper into genomics, it's back to biology. If these cave people weren't some radically different lineage, what else could twist bones toward the edge of known human variation? Disease, developmental quirks, hard lives lived in the tail end of an ice age. To test the unknown species idea honestly, we have to walk through those options first. Bones are not blueprints, they're diaries. They don't just record what species you were born into, they record what happened to you on the way through life. Every fever, every broken limb, every hungry winter. Two people with the same genes can end up with very different skeletons if one grows up well-fed and safe, and the other grows up sick, injured, and chronically stressed. So before we start declaring this doesn't match any known human, we have to ask a much less dramatic question. Could this just be what ordinary human biology looks like when things go wrong? Start with disease. Some illnesses literally reshape bone. Not metaphorically, not subtly. They change its thickness, texture, and proportions in ways that can look archaic if you're not careful. Take cranial thickening. The moment you hear unusually thick skull, your brain may jump to Neanderthals or other ancient hominins with heavy brow ridges and robust crania. But in modern humans, you can get dramatic thickening from conditions like anemia, certain endocrine disorders, chronic infections, or genetic diseases. In severe anemia, for example, your bone marrow goes into overdrive trying to make more red blood cells. That expansion can remodel the flat bones of the skull, creating a hair-on-end appearance on X-rays and visibly thickening the cranial vault. Some metabolic conditions add extra layers of bone to the inner or outer surface of the skull, inflating measurements that, in isolation, might look like an archaic trait. Then there's the jaw and teeth. Dental and mandibular anomalies are incredibly common in archaeological skeletons. You can see impacted canines that never erupted, extra teeth, missing teeth, asymmetrical jaws, severe crowding, or the opposite, wide dental arches with gaps. Chronic childhood infections, trauma to tooth buds, nutritional deficiencies, and simple developmental noise can all skew the lower face. Archaeologists sometimes find jaws with heavy flaring bone along the inside where chewing muscles attach. In a morphometrics plot that can push a specimen toward the Neanderthal side of the graph. But you can get similar patterns in modern people who habitually clamp, grind, or chew tough foods, or in jaws that have rebuilt themselves around missing teeth. Even something like a very receding chin, one of the classic archaic markers, shows up now and then in perfectly modern populations. If your reference sample is small or biased, a few chins like that can make a whole group seem odd. And then there are the big, rare conditions that really break the mold: skeletal dysplasias, dwarfism, gigantism. Think about achondroplasia, the most common form of dwarfism today. It shortens the limbs relative to the trunk, and changes the shape of vertebrae, alters the pelvis, and can affect the base of the skull. A person with achondroplasia in a prehistoric context, buried alone or poorly preserved, could easily be interpreted as not like the others. The ratios don't match typical Homo sapiens. The limb bones are too short and bowed. The foramen magnum is in a slightly different position. On a graph, that individual flies out toward the edge of known variation. Gigantism and acromegaly do something similar in the other direction. Excess growth hormone can lengthen long bones, thicken the jaw, enlarge hands and feet, and add coarse, heavy features to the face. If all you have is a fragmentary skeleton from 14,000 BC with unusually long limb bones and a massive mandible, the temptation to call it robust archaic is strong. But in each case, the critical phrase is in isolation. If you only look at a skull, not the rest of the body, if you only look at a femur, not the spine and hands, if you don't systematically check for the hallmarks of pathology, abnormal joint surfaces, irregular bone growth patterns, asymmetries, you can mistake disease for deep time divergence. Nutrition adds another layer. Bone growth is tightly tied to what you eat and when. Childhood malnutrition doesn't just make people smaller, it can change proportions. Stunted individuals may have relatively short limbs, narrow pelvic inlets, thinner cortical bone, or delayed fusion of growth plates. Periods of famine can leave lines in tooth enamel and subtle shifts in facial shape. Now imagine a group living at the very end of the Ice Age, riding out abrupt climate swings. Some cohorts grow up in relatively good times, others spend formative years during sudden cold snaps or failed hunting seasons. Over a few generations you can get a patchwork of body types, some tall, some short, some robust from high activity and protein-rich diets, others gracile and undergrown. If your excavation happens to recover more of one type than another, your picture of what these people were like can be skewed. It might even look like two different populations, or like a single weird lineage, when you're actually just seeing the fossilised echo of boom and bust childhoods. On top of individual pathology and nutrition, there's population-level adaptation. Humans are plastic, but we're also local. Over thousands of years, groups adapt genetically to their particular environments, and those adaptations can make them look other to an outside eye, even if they are fully boringly Homo sapiens. Cold-adapted bodies, for instance, tend towards stockier builds with shorter limbs and larger trunks. This reduces surface area relative to volume and helps conserve heat. Neanderthals are the textbook example, but similar patterns show up in modern Arctic populations. Thick chest walls, broad ribs, strong limb bones from moving in heavy clothing and over difficult terrain. All of that can push a late glacial population's skeletons toward the robust, archaic end of a comparison simply because they're living in a similar climate. High-activity lifestyles do the same. If you spend your life walking long distances, hauling loads, climbing, throwing, scraping hides, butchering animals, your bones respond. Your muscle attachments grow more pronounced. Cortical bone thickens in shafts under repetitive stress. Joints remodel to distribute unusual loads. Put someone like that next to a 21st century office worker in a morphometrics study, and they will not overlap neatly. Yet genetically, they could be almost identical. This is why paleoanthropologists and forensic anthropologists use something called differential diagnosis. They don't just look at a weird trait and ask, what species does this resemble? They build a mental checklist that goes more like, what are all the possible causes of this feature? Which are most likely, given what we know about humans? Which would leave other signs somewhere else in the skeleton? If a cranium looks thick and primitive, they check, is the thickening even or patchy, on the inside or outside? Are there changes in the long bones that match a systemic condition? Do the teeth, sinuses and jaw show patterns typical of a known disease? If a femur is unusually curved or massive, they ask, is this curvature symmetrical with the other leg? Could it be from a healed fracture, from rickets, from habitual squatting or kneeling, from a specific genetic disorder? If proportions are extreme, really short limbs, really long arms, narrow chest, odd vertebrae, they go hunting for the diagnostic constellation of a skeletal dysplasia, not just tick a box that says outside modern range. And critically, they don't do this in a vacuum. They compare the individual to others from the same site and time. If you find one massively robust individual among 10 fairly typical ones, the null hypothesis is not new species. It's, that's a particularly big, strong, maybe pathologically unusual person. You only start talking about population-level difference or separate lineages when the pattern repeats across multiple individuals, ideally across multiple sites, all dated to consistent time periods, all showing the same unusual suite of traits. This is where context saves you from overinterpretation. Imagine opening a cave layer and pulling out half a dozen partial skeletons. 2 have thick skulls and heavy jaws, 3 look within the known range of late glacial Europeans, 1 shows asymmetrical limb length and spinal anomalies. If you cherry-pick the 2 thick skulls and 1 odd spine and ignore the rest, you can tell a great story about a vanished lineage. If you do proper differential diagnosis, you're more likely to say, this was a normal late Pleistocene human group with some individuals who are sick, stressed, or just particularly robust. None of this means there are no strange lineages. Denisovans were real. So were the tiny people of Flores. We do occasionally stumble across bones that genuinely sit outside our current categories. But the bar for that claim is high. You need consistency across individuals. You need traits that don't match known pathological patterns. You need clear dating and stratigraphy to show you're not mixing remains from very different times. Ideally, you have genetic data that supports a deep divergence. Extraordinary anatomy by itself, A jaw that looks too strong, a cranium too thick, a femur too short, is not enough. Bones are diaries, and sometimes they're diaries of illness, hardship, or unusual lives written into an otherwise ordinary human population. So before we move on to the idea of truly other humans in this cave, we have to check that we're not just reading pathology as prehistory, or mistaking adaptation for alien. And there's one more mundane force we haven't talked about yet, one that can make any site's anatomy look stranger than it really is, the way bones get mixed, moved and misread long after their owners are gone. That's where we're headed next. Bones don't just lie there quietly for 14,000 years, waiting for us to come read them like a neatly filed archive. They get kicked, gnawed, washed, cracked, glued, mislabeled, and occasionally fixed into shapes they never actually had in life. So even if you've ruled out disease, malnutrition, and normal human adaptation, there's another question you have to ask before you start talking about a lost human species in a cave. Are these skeletons even real skeletons anymore? Or are we looking at a jigsaw puzzle that's been mixed with pieces from other boxes? Let's start with the simplest problem: mixed deposits. When archaeologists talk about a find, it's very tempting to imagine a single individual lying more or less where they fell, with all the bones more or less together. But most prehistoric cave deposits are not like that. They're more like a compost heap that's been disturbed for centuries. People camp in the entrance, animals drag in carcasses to eat, floods wash in sediment and bones from outside, collapsing ceilings dump rocks that crush, scatter, and rebury whatever was there before. Over time, you don't get a burial. You get layers of fragments from many individuals and many species, all jumbled together by gravity, water, and teeth. If you're lucky, you can still tease apart which bones belong to whom. You can match left and right femurs by size, look for articulating joints that fit together, and use radiocarbon dating to check that bones you think belong together are actually from the same window of time. But if you're not careful, or if the site was dug decades ago with less strict methods, it's very easy for bones from different individuals, and even different centuries, to be merged into one skeleton. Imagine this scenario. You have a partial skull from a layer around 14,000 BC. Nearby, in slightly higher sediment, there's a robust jaw from 11,000 BC. A century ago, an excavator pulls them both out of the ground, notices they're roughly the same size, and decides they must belong together. He reconstructs one head. On paper, you now have a single individual with a cranial shape, typical of late Ice Age humans, and a jaw that looks oddly massive and archaic, because it actually belongs to a later population with a different diet and activity pattern. Push that through a morphometrics pipeline and you get a chimera, a made-up skull that doesn't really match anything in the reference sample. Not modern, not Neanderthal, not anything. From there, unknown species is only a couple of enthusiastic conference talks away. Now multiply that by dozens of fragments. Add in the fact that juveniles and adults are often mixed, that animal bones can look eerily similar to human ones when they're broken just right, and suddenly that one weird cave starts to look less like a lost lineage and more like a messy attic. This brings us to misidentification. Human versus not quite human is trickier than most people think. A partial piece of long bone broken in the middle of the shaft can look very similar across multiple large mammals: horse, deer, cow. And human femur shafts can all produce cortical fragments that, in isolation, are hard to tell apart without training, or without microscopic and chemical tests. Some animal bones mimic specific human parts. Bear paw bones, for example, can superficially resemble human hand bones. Pig teeth can be mistaken for human molars if they're worn and broken in the right way. A small fragment of a juvenile mammal skull can be misread as part of a human child's cranium, and juvenile human bones are a whole problem by themselves. Children's skeletons are not just smaller adults, Their bones are softer, more porous, and full of growth plates that haven't fused yet. The shapes are different, the proportions are different, and the regions that will later fuse into a single bone can still be separate pieces. Take a developing skull. The bones are thinner with open sutures, and the base is still changing shape as the brain and face grow. A fragment from that base can look utterly alien compared to an adult reference series. The risk is that you compare a distorted juvenile piece to a clean adult dataset, find no neat match, and declare it outside the range. Distorted fossils add another layer. Time is not kind to bone. Caves routinely compress and warp remains in ways that would make any 3D scanner cry. This is where taphonomy comes in, the study of what happens to remains from the moment of death to the moment of discovery. Picture a body buried in a shallow pit in a cave floor. Over centuries, sediment piles up on top. The weight of that sediment slowly presses down. The cave roof shifts slightly from freeze-thaw cycles. Groundwater seeps through, with dissolving some minerals and depositing others. The skull doesn't just sit there, it flattens. The cranial vault may bow out. The face might shear slightly to one side. If the sediment compacts unevenly, you can end up with one half of the head pushed upward and outward while the other half is relatively protected. On top of mechanical distortion, you get chemical change. Mineral replacement can thicken some areas and thin others. Pores fill in with calcite, changing the apparent density and surface texture. The outer table of the bone can erode away, leaving the inner table exposed, which looks like a strange, pitted, spongy surface, unlike any normal human skull. Take that warped, chemically altered object, scan it, and compare it blindly to pristine modern skeletons, and of course it looks weird. You're not comparing like to like. You're comparing a crushed, stretched, mineralized relic to a clean medical specimen from 1972. If you don't explicitly model taphonomic distortion, you can mistake geological damage for anatomy and post-mortem warping for evolutionary difference, and that's before we even talk about reconstruction. Some of the most famous odd skulls in the history of paleoanthropology turned out to be victims of over-enthusiastic reconstruction. When you pull a cranium out of a cave, it is almost never intact. It's a cluster of pieces, vault fragments, bits of face, maybe a section of the base. Somebody has to put Humpty Dumpty back together again. Depending on when the work was done, that somebody might have been using modelling clay, plaster, wire, and a decent dose of guesswork. There are a few classic ways this goes wrong. Pieces get mirrored. A left frontal bone fragment is mistakenly placed on the right side. A bit of parietal is rotated 180 degrees. The overall shape of the brain case is subtly, or not so subtly, altered. Gaps get filled. Where pieces are missing, the restorer might sculpt in the most reasonable missing bits, sometimes based on expectations about what the skull should look like. If they're primed to see Neanderthal-like features, they may rebuild heavier brow ridges. If they expect modern humans, they may smooth and round. Thickness gets misjudged. When vault fragments are set into plaster, the apparent wall thickness can be increased or decreased depending on how deeply they're bedded. Measurements taken later can record that artificial thickness as if it were real. Even the angle between facial bones and the base of the skull, a key diagnostic trait in many species comparisons, can be thrown off by a few degrees if the reconstruction tilts one piece slightly to make it fit better. Once these reconstructions are done, they harden, literally and intellectually. Later researchers might take calipers to them as if they were intact fossils. They scan them, publish them, build datasets around them. Only much later, sometimes decades later, does someone take the whole thing apart, refit the pieces with more precise methods, and realize that odd shape was an artifact. So, if we want to know whether the cave's strange bones really represent a vanished human type, we need to systematically rule out all of these more mundane possibilities What would that actually look like? First, re-excavation, or at least reanalysis of the site's stratigraphy. You'd want high-resolution mapping of where every fragment came from, layer by layer. If older excavations were sloppy, you might open new trenches in undisturbed sections, using modern methods, fine-grained sediment analysis, careful recording of bone orientations, microstratigraphy. You'd compare the new material to the old. Do the same weird traits show up in securely undisturbed layers, or do they cluster in deposits that show signs of mixing and disturbance? Second, rigorous sorting of individuals. You'd lay out all bones by size, side, and age. Use osteological criteria to match left and right elements, articular surfaces, and proportional relationships. When in doubt, you treat fragments as unassigned rather than force them into a composite. Then you date strategically. Radiocarbon or other appropriate methods on multiple bones that were previously assumed to belong to a single individual. If the jaw and the cranium that were glued together turn out to be 1,000 years apart, that composite goes straight into the chimera bin. Third, systematic identification checks. You'd bring in zooarchaeologists, specialists in animal bones, and ask them to go through the supposed human fragments blind. Anything that might be deer, bear, pig, or anything else gets pulled, tested, and only admitted to the human sample if it passes detailed morphological and ideally microscopic scrutiny. You'd pay particular attention to juvenile bones, comparing them to modern growth series, not just adult skeletons, to avoid misreading developmental stages as alien morphology. Fourth, taphonomic analysis. Geologists and taphonomists would examine fracture patterns, compression marks, mineralization fronts, and deformation directions. You can sometimes reconstruct how a skull was squashed by looking at microcracks and bending lines. With modern 3D modeling, you can even attempt digital uncrumpling, warping a distorted fossil back toward a more symmetric, undistorted shape. Measurements taken on that corrected model can be very different from those taken on the raw, crushed specimen. Fifth, reconstruction audits. Where older reconstructions exist, you'd CT scan them, distinguish original bone from filler material, and if possible digitally separate the two. You'd check for mirrored parts, misaligned sutures, and unnatural symmetries. In some cases, you might physically dismantle the reconstruction and start over, using modern adhesives, minimal filler, and explicit documentation of every assumption you make. Only after all of that, after you've stripped away mixing, misidentification, distortion, and human improvements, do you go back to the evolutionary question. What remains when the noise is gone? Do you still see a coherent, repeated pattern that doesn't fit any known human population? Or do the anomalies evaporate into a handful of ordinary people in an ordinary late glacial cave? Because if that pattern survives this kind of scrutiny, if, after you've checked every boring explanation, you still have multiple individuals from the same time, and with the same suite of unusual traits, then the story changes. Then we're no longer talking about mistakes or misread diaries. We're talking about the possibility of a real late surviving human lineage that seems to vanish from the record right after 14,000 BC. That's the idea we're going to explore next, not because it's the most dramatic story, but because once you've been ruthless with the mundane explanations and they still don't fit, you're allowed to ask the big question, what if there really was someone else in that cave? So let's take the brakes off for a moment and follow that question all the way out. Suppose we've done the boring work. The site's been re-excavated. The stratigraphy is tight. The individuals are actually individuals, not Franken assemblies. The animal bones are out. The juveniles are correctly identified. The taphonomic distortion is modelled. The old reconstructions have been dismantled and rebuilt. And after all that, there's still a pattern. Multiple people, all from around 14,000 BC, all from the same cave system and nearby sites, all showing a consistent package of traits that doesn't sit comfortably inside any known late Ice Age human group. Not just one odd skull, but a cluster. Not scattered anomalies, but a signal. What would that actually mean? First, it doesn't automatically mean new species. The story we like to tell is simple. There were Neanderthals, there were Denisovans, then there was us. They disappear, we stay, roll credits. But human evolution was never a neat family tree. It's more like a tangled bush that someone drove a truck through. Branches break, regrow, fuse back together. We already know this from genetics. When scientists started sequencing ancient DNA, they didn't just find traces of Neanderthals and Denisovans in us. They found something else. Actually, multiple something elses. In several modern African populations, there are chunks of DNA that don't match any known archaic genomes. They're too divergent to have evolved since our common bottleneck. But they're not Neanderthal, not Denisovan, not anything we have fossils for. Geneticists call these ghost lineages. Human groups that clearly existed, clearly interbred with our ancestors, but have left no unambiguous bones we can point to and say, that's them. It works the other way too. When Denisovan DNA was first sequenced from a pinky bone in Siberia, it didn't match any known species either. For a moment, Denisovans were themselves a ghost lineage brought to light by a lab machine instead of a jaw in the dirt. Now flip the script. Imagine the cave's strange people are the opposite. A morphological signal of a group we haven't yet seen in the genomes. A local, late Ice Age population that was genetically close enough to us to interbreed, but distinct enough in its history and environment to look, on the skeleton, like an outlier. So what would we need to elevate that from weird population to lost lineage? There are a few levels here. At the most conservative level, you might say, these are just a poorly documented regional variant of late Upper Paleolithic humans. Maybe they lived in a marginal environment. Maybe they had a peculiar diet or a long period of isolation, or went through their own small bottleneck. In that case, their skeletons might show consistently different limb proportions, unusual robusticity or gracility in certain bones, slightly different cranial vault shape or facial proportions, but still within the outer edge of what a generous global human dataset could contain. They'd be a distinct population, but not necessarily a taxonomic event. To move beyond that, toward lineage, you'd want a few things. First, repetition. You'd need multiple individuals, ideally from multiple sites, all in the same time range, all showing the same constellation of traits. Not one person with a strange jaw, but tens of people with the same jaw-vault-pelvis pattern. Second, coherence. Those traits should make sense together developmentally and functionally. You'd expect consistent differences in the way the skull base is angled, the way the teeth are set in the jaw, the way the limb joints are shaped. Not a random grab bag, but an integrated anatomy. Third, separation. You'd want clear statistical separation from contemporaneous groups. When you run morphometric analyses, these folks should cluster together and away from known late glacial Europeans, early Near Easterners, or whatever nearby populations you compare them to. And fourth, if we're dreaming big, genetics. Ancient DNA, or at least ancient proteins, that show they're not just a quirky branch of some already sampled group, but have their own distinctive evolutionary history. Maybe they share some ancestry with known Ice Age Europeans, but also carry deep divergences that suggest a long period of isolation. Now, new species is an even higher bar. Species isn't just about looking different, it's about patterns of gene flow and reproductive compatibility. And with humans, those lines are very fuzzy. Neanderthals and modern humans were morphologically distinct enough that if you put their skeletons on a table, even a good student could tell them apart. Broad faces, barrel chests, short, heavily built limbs, distinctive cranial features, and yet we interbred with them successfully, enough that most people alive today carry Neanderthal DNA. So even with that level of difference, many researchers prefer to treat Neanderthals as a subspecies, or at least as very close relative species with incomplete reproductive isolation. For our cave people to be bumped all the way up to new species, you'd want a stable, well-defined suite of skeletal traits clearly outside the known human range, not just on one measurement, but across the body. Evidence that these traits persisted over many thousands of years and across multiple sites. Ideally, genetic evidence showing a deep divergence from other lineages, on the order of hundreds of thousands of years like we see between us and Neanderthals. And even then, there would be arguments, because if they lived to 14,000 BC, and if modern humans were nearby, we probably met them. And if we met them, we probably mixed. Which brings us back to something more interesting, and maybe more realistic. A late surviving, regionally isolated lineage that was different enough to notice, but not different enough to be totally alien. How do you get a group like that? And isolation and accidents of history. Imagine a small founding group moving into a tricky environment at the edge of the ice sheets, or on a peninsula that's easy to walk into and hard to walk out of once sea levels rise. They get cut off. Their population stays small for thousands of years. They go through one or more bottlenecks where only a few families contribute most of the genes to the next generation. Geneticists call this the founder effect. It's like shuffling a deck of cards and then only dealing from the top 5. Whatever weird combinations come up there can become the norm in that population. Over time, this can shift things like average height and limb proportions, cranial shape, including how wide or tall the vault tends to be, robusticity of jaws and brow ridges, pelvis shape and birth canal dimensions. Throw in a slightly different diet, maybe more reliance on hard seeds or heavy use of teeth as tools, and you add localized wear patterns and bone remodeling on top of that genetic background. From the outside, from 14,000 years away, the result can look like they're not quite us. But they are us, in the sense that they're part of the same messy interbreeding late Pleistocene network. They're just a branch that grew in the dark for a while. If we confirmed such a lineage, what would that change? First, our migration maps would get more complicated. Right now, we draw big arrows out of Africa into Eurasia into the Americas. Maybe a few side arrows into dead ends. A confirmed late Ice Age lineage would force us to acknowledge that even as the ice was retreating and modern humans were consolidating their range, our family tree still had side branches. Pockets of people who had their own history, their own adaptations, and their own end. Second, it would change how we talk about human diversity. It's easy to think of human variation as something that happens only within a single, continuous species after 50,000 BC, mostly reflected in skin color, body proportions, maybe some disease resistance genes. But a late surviving lineage would show that deeper morphological diversity, skulls, jaws, overall body plans, overlapped in time with the very cultures we usually present as the dawn of us. Your mental picture of a late glacial campfire might have to include people whose silhouettes were subtly but noticeably different. Third, it would sharpen the question of disappearance. If a distinct lineage makes it all the way to 14,000 BC, then vanishes, we have to ask, why then? Was it climate? As the Ice Age ended, did their specific adaptations become a disadvantage? Was it competition? Did incoming or expanding modern human groups outnumber, outtrade, or outfight them? Or was it absorption? Did they simply get genetically swallowed? Their distinct traits diluted over generations of interbreeding until only faint echoes remain in local populations. Finally, it would change the emotional tone of our origin story. Instead of a clean handoff from archaic humans to modern humans, we'd have to accept that our world was, until shockingly recently, shared with other kinds of people. Not Neanderthals in some deep, safely distant past, but neighbours living in familiar landscapes, under skies and climates not so different from our own. And somewhere, in our genomes or in their caves, might still be traces of that meeting. If the strange bones in this cave really do belong to a lost late Ice Age lineage, then 14,000 BC stops being just another date on a climate graph. It becomes the moment when one of the last alternative human stories fell silent, which raises an uncomfortable follow-up. If they vanished from this cave, how exactly did they vanish? Vanished sounds final, like somebody hit a cosmic off switch. But when archaeologists say a group vanishes from the record, they usually mean something much less dramatic and much more frustrating. We stop seeing them. That can mean a few different things. At the smallest scale, vanished can just mean they stopped using this one cave. Maybe the lineage kept going in the valley or on the next ridge over, or 2 days' walk downstream. The bones just aren't here anymore. At a wider scale, it could mean they were absorbed. The people who carried this unusual body plan met larger, more mobile groups, married into them, and over a few hundred years their distinct features blurred into the background variation of the region. And at the far end of the scale, yes, it can mean extinction. The last people with this particular combination of traits and history died without leaving a distinct, traceable descendant population. There's also a fourth possibility that scientists don't like to say out loud because it's unsatisfying but very real. The evidence is just gone, or we haven't found it yet. So when we stand in that cave at 14,000 BC and the trail goes cold, those are the 4 doors in front of us. Local abandonment, assimilation, extinction, or simply loss of the trail. Which one makes sense here? To answer that, you have to look at what 14,000 BC was doing to everyone. This wasn't a quiet, stable time. It was the tail end of the last ice age, a period when climate didn't just change, it lurched. In the 1,000 years before and after our date, temperature curves in Greenland ice cores zigzag like a seismograph. You get abrupt warm pulses, followed by chilling reversals like the older Dryas. Glaciers retreat, then stabilize. Forest belts creep north, then stall. Every one of those swings rewrites the rules on the ground. An open, grassy steppe rich in migrating herds can turn into a patchwork of shrubs, wetlands, and closed forest. Animals you relied on shift their migration routes, or shrink in number. New competitors, both animal and human, move into newly productive areas. If you're a small, specialized group sitting on the margins of a glacier, what happens when the ice pulls back and the landscape reorganizes? You can imagine a few scenarios. In one, the world gets better. For everyone else, bigger. More flexible groups from the south move into the now nicer landscape. They bring different toolkits, maybe different social networks, maybe a slightly different way of carving up territory. They don't have to wipe you out. They just outnumber you. They have more marriage partners, more hunters, more people to scout, trade, and defend. Your daughters and sons marry into them, your distinct features get averaged out, and within a handful of generations, nobody looking at the bones can draw a clean line around your people anymore. That's assimilation. In another scenario, the climate swing hits in the opposite direction. You're already living near the edge of what your local ecology can support. A cold snap hits, or the rains shift just far enough that a key river becomes less reliable. The wetland dries earlier, so the game herds reroute. Suddenly your just enough becomes not enough. In small populations, you don't need a Hollywood-scale disaster, a string of bad winters, a disease outbreak that kills more children than usual, a single generation where very few women survive childbirth, that can crash your numbers to the point where recovery is mathematically unlikely. That's extinction. but the slow, boring kind. No last stand. Just fewer and fewer fires in the distance each winter, until one year there are none, and threaded through both of those is competition. By 14,000 BC, modern humans with fairly standardized Upper Paleolithic toolkits are spreading across vast areas of Eurasia. Blade technology, microliths, complex hunting strategies, maybe more extensive trade networks. If our cave people are small, it's just a regionally isolated lineage with their own long history, they're suddenly sharing landscapes with groups who hunt the same animals, favour the same sheltered valleys and water sources, have larger social networks to call on in a crunch that doesn't automatically mean war. It can mean being priced out. Game gets skittish because of repeated hunting drives. The best flint sources are now owned by somebody else's kin network. The travel routes you used to take to follow herds are now crowded with strangers. You can move, you can merge, or you can dwindle. And layered on top of climate and competition, there's a wild card we can't see in the bones: disease. When previously separate populations meet, their microbes meet too. A pathogen that's a minor childhood illness in one group can be devastating in another with no prior exposure and no inherited immunity. We see this over and over in historic contacts between human populations. There is no reason to think the late Pleistocene was immune. A small, isolated lineage that encounters a much larger, more mobile network can be hit not just by new ideas and new tools, but by new diseases. Again, no apocalypse required. A few bad epidemics in a population of a few hundred can permanently alter its trajectory. All of that sounds dramatic. But there's another, much quieter possibility. Nothing happened to them, except a change in how they use this one place. Because caves are tricky. Many late Ice Age caves weren't year-round homes. They were seasonal camps, hunting bases, special-purpose butchering sites, ritual spaces or burial grounds. So ask a different question. What if this cave was never their village at all? Maybe it was a winter hunting shelter. They came here only during certain years when a particular herd passed through. As the climate shifted and migration routes changed, this spot fell off the map of practical shelters. They followed the animals, and the cave was simply not visited anymore. Archaeologically, that reads as they vanish from the cave. Or maybe this was a burial place. If that's the case, a change in belief could make the whole system disappear overnight. A charismatic leader has a dream, a shaman has a vision, a clan feud breaks out, and suddenly this cave is taboo. No one is buried here anymore. The dead go elsewhere. To us, thousands of years later, that looks like a population event. To them, it might have been one new song, one new story, one new rule. Even more extreme, this could have been the site of a one-time catastrophe or ritual event, an epidemic quarantine, a mass burial after a landslide, a single group sheltering here during a particularly brutal winter who never returned. The skeletal population in the cave could be a snapshot of a disaster, not a cross-section of an entire lineage over centuries. In that case, asking why did they vanish from the cave is like asking, why don't we see more Titanic passengers after 1912? You're looking at the wrong level. The cave event is the end, not the norm. And then there's the most annoying explanation of all. They didn't vanish. Our ability to see them did. The archaeological record is brutally biased. Caves preserve things well, which is why we love them. But most human life in 14,000 BC wasn't happening in caves. It was happening in open-air camps, river terraces, forest edges, coastal plains. Those are the exact places that get hammered by erosion and river migration, freeze-thaw cycles that break and scatter bones, soil acidity that dissolves organic material, landslides and slope wash that remix layers. Add in one more huge factor, sea level rise. At the end of the Ice Age, global sea level rose by more than 100 meters. Huge stretches of what were once habitable coastal plains are now underwater. If our cave people favoured shorelines, estuaries, or low river deltas, a big part of their story is literally beneath the waves. Their missing sites might be perfect settlements with hearths, tools, and burials, lying on a drowned shelf we've barely begun to survey. Even on land, the map of what we know is shaped by where people have looked. Road projects, quarries, dam constructions, and a few lucky surveys create a patchwork of discovery. Whole regions can be archaeologically dark simply because no one has dug there with the right questions in mind. So the silence after 14,000 BC might not be the silence of extinction. It might be the silence of unexcavated valleys and unscanned seabeds. That's the uncomfortable reality. At this distance, those four explanations blur into each other. Some local abandonment, some assimilation, maybe some true extinction, and a giant shadow cast by everything we haven't found yet and maybe never will. But the story doesn't have to end with a shrug, because our tools for listening to that silence are getting better. Ancient DNA is one obvious frontier. Methods keep improving for pulling genetic material out of highly degraded bone and even directly out of sediments. It's now possible, in some cases, to detect the presence of humans in a layer even when no bones are visible at all. Proteomics, analysing ancient proteins, pushes that even further. Proteins survive in conditions where DNA is long gone. A single fragment of tooth enamel from an unidentifiable individual could one day tell us whether they were part of a distinct lineage or just a quirky variant of a known group. On the landscape scale, remote sensing is opening new doors. LIDAR and other scanning technologies can strip away vegetation cover to reveal buried terraces, cave entrances, and subtle earthworks. Underwater archaeology is finally starting to probe those drowned coastal shelves that used to be Ice Age shorelines, and in the lab, morphometric techniques are becoming more sensitive. Machine learning algorithms trained on huge datasets of human and non-human bones can flag subtle shape differences our eyes gloss over. A fragment that looks ordinary under a hand lens might, in a high-dimensional shape analysis, light up as belonging to the same odd cluster as the cave people. Put all of that together, and the apparent full stop at 14,000 BC starts to look less like the end of a sentence and more like an unfinished paragraph. Somewhere out there, in a muddy riverbank, under a farmer's field, in a submerged cavern on a continental shelf, there may be another site, another set of bones, another glimpse of this late, strange branch of our family tree, maybe a little earlier, maybe a little later, maybe showing us whether they faded into us or away from us. Until we find it, this cave is our only line of dialogue with them. The question is whether it's the last line or just the first whisper of a story we haven't fully uncovered yet. So where does all of this leave us? If we strip away the headlines, the clickbait graphics, and the temptation to crown a new human species every time a bone looks weird, we're left with a quieter, much stronger set of takeaways. First, there really was something odd in that cave. Measured carefully, those bones don't line up perfectly with any single known population. They sit at the edge of the variation we're used to, combining traits in a way that makes specialists pause. The dating, as far as our current tools allow, really does point to a late Ice Age context, somewhere around 14,000 BC. That's the known part. Second, doesn't fit neatly, is not the same as isn't human. We've seen again and again how pathology, growth stage, and simple human diversity can produce skeletons that look alien until you zoom out and compare them to a big enough sample. We've seen misdated layers, mixed deposits, and animal bones masquerading as something stranger. We've seen how ancient DNA can flip the story on its head, or refuse to show up at all. That's the uncertain part. And third, even among people who specialize in this stuff, there is real debate. Some researchers lean toward a small local population with a slightly unusual body plan, maybe a lineage with deep roots, and are hanging on in a marginal pocket until the end of the Ice Age, then being absorbed into larger human networks. Others leave the door cracked for something more radical, a late surviving branch, a ghost offshoot of that earlier human radiation that managed to persist into a time we thought belonged only to us. No one can honestly say we've proven that. No one can honestly say we've disproven it either, and that's the part that keeps this cave alive. Because you don't need a dramatic, cinematic answer for this to be profound. A handful of bones, in the right layer, with the right mix of traits, is enough to tug at the edges of the tidy timeline we carry in our heads. We like to imagine prehistory as a clean sequence. First them, then finally us. But the deeper we look, the more it starts to feel like overlapping echoes. Populations splitting and rejoining, lineages thinning to a thread, and then flaring back through interbreeding, small pockets of difference hanging on longer than we expected. This cave is one of those echoes. It might be the last flicker of a long, quiet branch of our family tree. It might be a snapshot of ordinary humans living an extraordinary marginal life at the end of the Ice Age. Either way, it's a reminder that the story of us is not finished just because we've written neat labels on a few skulls in museum drawers. Right now, the mystery is still breathing in the dark. It lives in that gap between what the bones suggest and what the data can actually prove. It lives in the sediments we haven't sampled yet, the underwater plains we haven't mapped, the open-air sites that look like just another field until someone digs with the right questions, and it lives in our curiosity. So I'm going to hand this back to you. If you had to bet, based on everything you've heard, what do you think happened to the cave people? Were they a strange but fully human local group who got folded into larger populations? A late, fragile offshoot of some older human lineage, finally losing their last refuge? Or are we just staring at a statistical oddity in a sample size that's way too small? Tell me your theory in the comments, and while you're there, let me know where you're listening from and what time it is for you right now. Are you in a city glowing at midnight, half asleep with this playing in the background? On a long commute as the sun comes up? Curled in bed, somewhere far from caves and ice and mammoth bones? I read those, and they're a strange modern mirror to the networks we've been talking about. Voices scattered across the planet still trying to make sense of the same ancient questions. If you enjoyed wandering down this rabbit hole, it helps a lot if you tap like, drop a comment and subscribe so you don't miss the next dive into deep time. That simple feedback tells the algorithm that this kind of slow, careful storytelling is worth sharing with more people. And if you want to keep going even deeper into these prehistoric secrets, I've put together a book that pulls together some of the strangest, most revealing stories from before history, from real bottlenecks to ghost populations and everything in between. You can read more about it and pick up a copy over at sleepytimehistory.com. However you leave this story, convinced, skeptical, or deliciously undecided, remember, somewhere under our feet there are still bones we haven't met yet. And one day, in some other cave, someone will brush the soil away from a fragment of skull, or tooth, or finger bone, and the neat timeline will have to stretch again,